Hello, everyone. Thank you for being here today for our critical design review of Signflex. We are Group 28, and my name is Antonio Rez. Along with my teammates, we have been working on developing a wearable smart glove that translates American Sign Language into text and speech in real time. Our team consists of 4 members from different engineering disciplines: Esteban Reyes, electrical engineering; Madison Vasser, electrical engineering; Ryan Rahrouf, computer engineering; and myself, computer engineering. So what exactly is Signflex? Signflex is a wearable smart glove that translates American Sign Language gestures into real-time text and speech. It helps ASL users to communicate with people who don't know sign language. This glove is designed to be easy to use, accurate, and providing instant translation without needing an interpreter or extra tools. Signflex make communication faster and more accessible for everyday interactions. The motivation behind our project is rooted in the communication barriers that exist for individuals who rely on ASL. In the United States alone, 6.4 to 7 million adults use sign language to communicate. However, ASL is not widely understood by the general population, making everyday interaction in workplaces, education, and public spaces very difficult. ASL is the third most commonly used language in the United States. Yet, there are limited technological solutions that can provide real-time ASL to speech translation. Current communication methods often rely on interpreters or text-based solutions, which are not always available or convenient for real-time conversations. With Signflex, we aim to create an interactive, wearable, and efficient system that allows ASL users to communicate more freely and independently in real-world situations. To address these challenges, we have developed the Signflex, which is a smart glove that offers a real-time translation solution for ASL users. Our system provides a smart glove embedded with flex sensors, an accelerometer, and a camera to capture ASL gestures, an Android app that displays recognized gesture in real time and convert them into speech, Bluetooth connectivity for seamless communication between the glove and the mobile app, LED indicators on the glove that provides immediate feedback, letting the user know if their gesture was successfully recognized. This technology has the potential to encourage more people to learn ASL while also making the communication inclusive in various environments such as schools, workplaces, and public services.
The goals and objectives of the Signflex project include the basic goals, advanced goals, and objectives. For our basic goals, to develop a smart glove for real-time American Sign Language detection, display recognized gestures on an Android app, ensure seamless Bluetooth communication between glove and application, and provide a user-friendly interface for the ease of accessibility. Our advanced goals include integrating computer vision for enhanced recognition accuracy, implementing machine learning models to improve our gesture classifications, optimize Bluetooth transmission for low latency, and enabling gesture customization for personalized recognition. Our objectives include providing real-time feedback via LEDs to users on gesture recognition, developing a mobile app that will seamlessly connect to Signflex, maintaining comfortability, wearability, and flexibility for extended periods of use, detecting and interpreting gestures involving finger movement and hand orientation, as well as displaying battery status to alert the user when the battery is low and the glove needs to be put on charge. For the Signflex team's engineering specifications, we chose the following: size, weight, sensor sensitivity, temperature range, power consumption, memory usage, processing speed, cost, and accuracy. For our top 3 specifications, we chose power consumption, processing speed, and accuracy, as these 3 are going to be the most crucial to our project success. For power consumption, we must not exceed 500 megawatts. For processing speed, we must have 200 milliseconds, and for accuracy, we must have at least 95% accuracy for our gesture recognition. Now we will discuss the hardware comparison and selection for our Signflex project. For our hardware block diagram, this shows the flow of the system of the Signflex Smart Glove. As you can see, we chose the power supply to be a lithium-ion battery that will also require a 5-volt buck converter and a 3.3 linear voltage regulator, as we have multiple voltages needed for the different components in our system. The 5-volt regulator is for the flex sensors, as they do not properly function without 5 volts. And our 3.3 linear voltage regulator is for our battery monitoring system, our ESP32, and our accelerometer. Once all the data is received from these components via the ESP32, it will then be transmitted via Bluetooth to the smartphone and camera for image processing and gesture recognition. For our peripheral devices, we had to choose between an FPGA and an ESP32. An FPGA is a field programmable gate array that is a hardware reconfigurable device and allows for us to create custom digital circuits. Unlike traditional processors, it supports parallel processing, making it ideal for high-speed tasks like AI and real-time image processing. However, they require HDL programming using Verilog or VHDL, making the development a bit more complex than we need for our project. The ESP32, on the other hand, is a fixed architecture microcontroller that can run on C or C++. It processes the tasks sequentially but comes with built-in Wi-Fi and Bluetooth, making it perfect for IoT and embedded systems. It's power efficient, easy to program with Arduino, and it's cost effective, making it a great choice for general purpose applications. As stated previously, microcontrollers are more suitable for our project than FPGAs, as the FPGA would be overpowered for this application. Microcontrollers are more cost-effective and easier to program with C and C++. The integrated library simplifies sensor and communication module handling, and they're also designed to be low power, which is crucial for our project, as we have an engineering specification to meet. Integrated ADC will also convert the analog data from the flex sensors, making this the ideal choice for our project. For our microcontroller selection, our team decided on the ESP32 Room D. It offers low power consumption, making it ideal for battery-powered applications. With built-in Wi-Fi and Bluetooth, it also enables seamless wireless communication. The 240 MHz CPU provides enough processing power to efficiently handle real-time sensor data management, ensuring smooth operation. It's a low-cost solution, making it both practical and budget-friendly for our needs. For our peripheral devices, our team is utilizing flex sensors. The flex sensors work like a potentiometer, changing the resistance as the user moves their fingers to make gestures. This varying resistance is then transmitted to the microcontroller, where it's processed and converted into signals that represent specific American Sign Language letters. Essentially, it detects the bending motion by adjusting resistance based on the degree of flexing, allowing us to accurately capture hand movements for sign language recognition. For our project, the Spectra symbol flex sensors are the best fit due to their high durability and compatibility with wearable technology. To ensure accurate detection across different hand sizes, we opted for both the 2.2-inch and the 4.5-inch sensors, allowing us to accommodate for those with larger fingers and maintaining precision and gesture recognition. Along with larger fingers, we can use the 2.2-inch for the thumb and the pinky, and the 4.5-inch for the index, middle, and ring finger. For our next peripheral device, our team is utilizing an accelerometer. The accelerometer tracks movement and positioning in three-dimensional space by measuring the rate of change in its velocity. It works alongside the flex sensors to detect and interpret hand movements, including tilting, rotating, and forward-backward motions. This will enhance the ASL gesture translation by capturing more complex movements, significantly improving the system's accuracy and effectiveness. Additionally, it will measure the acceleration forces, whether static, like gravity, or dynamic, such as movement and vibrations. For our accelerometer selection, our team decided to go with the LSM6D S3CR as it's the best choice for Signflex. One of the key reasons is its low power consumption, as it uses only 0.9 milliamps in active mode, making it the most efficient choice for our battery-powered system. Additionally, it's a compact size, making it ideal for wearables and ensuring a comfortable design. It also provides a wide sensitivity range that allows us to track precise hand movements with high accuracy. The data rate gives us a good balance between performance and efficiency. With an operating voltage of 1.7 volts to 3.6 volts, it's fully compatible with our system, and its mid-range price makes it a cost-effective solution without compromising functionality. All of these factors make it the best choice for ensuring smooth, reliable, and energy-efficient motion tracking in Signflex.
The battery selected, which will make up the power supply unit, will be lithium-ion batteries due to their high battery capacity, which will allow the user to use the glove for an extended period of time. It also provides a better experience for the user in terms of comfort, since lithium-ion batteries are very lightweight compared to the other options. Some of the reasons why we are choosing the lithium-ion battery as well is because compared to their counterparts, it has a stable voltage output, which is what we want ideally for the sensors in a microcontroller, and it generates less heat compared to the other options. We will have two regulators, which will be responsible for distributing the power from the power supply unit over to the external components on the PCB. The buck regulator was chosen for the 5 volts due to its high efficiency rate, which means there will be a minimal power drain from the input voltage. And the specific buck regulator we chose has the ability to draw a very low current if set in low power mode. This helps us reach our goal to maintain a very low power consuming system. The low dropout linear voltage regulator will serve as a regulator which will supply the 3.3 volts. This type of regulator was selected because it has minimal electrical noise compared to other regulators due to the circuit being less complex, usually consisting of just a few capacitors, while switching regulators induce more electrical noise in the system due to the necessary switching of the current rapidly turning on and off in order to perform the voltage conversion. We will have two daughter boards which will clip on with male header pins into the female header pins located on the main PCB in order to distribute the power from the power supply unit. The LM2596T buck regulator will supply 5 volts for the flex sensors and act as the input voltage of the LDO regulator, while the AMS1117 LDO regulator will supply the 3.3 volts for the MCU, accelerometer, and battery monitoring system. Our main board is going to hold the MCU and external peripheral devices. The design behind the main board has a 4-layer plane instead of the standard 2-layer plane, because the 4-layer plane will allow the power planes to dissipate heat, while a 2-layer plane has no dedicated heat dissipation layers. A 4-layer plane also allows a cleaner and more reliable signal transmission for high-speed digital communication, which is very important for our project. Our PCB stackup has the top layer acting as a signal layer, first inner layer and bottom layer as the power planes, and the second inner layer acting as the ground. Our prototype consists of the flex sensors attached to the glove using electronic grade silicone, where they were tested in order to ensure their proper function with the help of an LED, as well as to make sure the silicone didn't damage the flex sensors and affect the performance. A successful result occurs when the flex sensors are bent at a certain degree. It passes a set threshold and then lights up the LED, as seen on the image shown on the left. We also have an armband which is responsible for holding the power supply unit in order to relieve excess weight on the user's hand and provide them a comfortable experience. We did face multiple challenges while traversing the development of this project. Our flex sensors were not functioning properly due to incorrectly building the setup based on the application circuit on the datasheet. We were a little bit confused on how to build it because the datasheet wasn't really clear and the layout didn't really make that much sense. So we had to do a little bit of research, and we found a YouTube video of someone actually recreating the application circuit on a simulation, and we recreated that simulation, and by copying it into the actual prototype, we're able to make it work. Another issue we had was that we weren't supplying enough voltage to the flex sensors. The data sheet specifically called out for 5 volts, but we were feeding it 3.3 volts mistakenly. but once we added those 5 volts, the flex sensors worked. Another issue that we had was that our original power supply unit was meant to be a power bank, but we had to switch over to the lithium ion batteries in order to properly use the battery fuel gauge system, which is on the main PCB. The battery fuel gauge system we have is meant for a single cell battery, while the power bank is a multi-cell battery system. So if we were to hook up the power bank to the current battery system, the fuel gauge will not be able to withstand the power, and in turn burn up and ruin the PCB board. If we were to move back to the power bank in the near future, we would have to replace the current fuel gauge system into a multi-cell fuel gauge system. But as of right now, we're going to keep what we have and complete the first iteration of our PCB board and see what results we can gain from this and move forward with. Another issue we had was that our project didn't have enough peripheral devices. We thought we could use a complete soldered accelerometer and hook it up to the PCB, but instead the accelerometer was built according to its data sheet and was integrated to the main PCB. And this helped us reach the requirement of the project in order to create a significant PCB design.
Now that we have covered the hardware components and how the glove captures gesture data, let's move on to the software. The software is responsible for processing sensor reading, applying computer vision, and translating ASL gestures into text and speech in real time. In addition to sensor-based gesture recognition, we incorporated computer vision to improve accuracy and flexibility. Computer vision allows Signflex to track hand movements using a smartphone camera, process images in real time, and classify gestures with AI-powered image recognition. To achieve this, we capture live images using a smartphone camera, use OpenCV for image pre-processing to enhance hand contours and clarity, leverage TensorFlow for gesture classification, ensuring precise recognition of ASL signs. This combination allows us to detect both static and dynamic gestures, improving overall system accuracy. We compared two potential platforms for image processing: Samsung Galaxy S7, a smartphone with a built-in camera and high processing power, and a Raspberry Pi 4, a single board computer capable of external camera integration, but with processing limitation. After testing both, we selected the Samsung Galaxy S7 because it provides a better image resolution for gesture recognition. It eliminates the need for an external camera. Using the smartphone built-in camera reduces system complexity while maintaining high accuracy. For gesture recognition, we evaluated two approaches: OpenCV plus TensorFlow Lite, which allows us to train our own model using images captured while wearing the glove, and also OpenCV enhances image quality before passing it to a custom trained deep training model for classification. On the other hand, MediaPipe Hands, which is a pre-trained model that detects bare hand landmarks but doesn't support gloves, making it unsuitable for our application. We selected OpenCV and TensorFlow Lite because we can train our own model specifically with the glove, improving accuracy, and use OpenCV that provides a better image pre-processing, reducing noise and enhancing features. For programming the ESP32, we needed an IDE that was easy to use and also supported sensor integration and was compatible with our real-time collection requirements. We compared two options: Arduino IDE, which is a simple and beginner-friendly, and also has a built-in libraries for our flex sensor and accelerometer, and a Visual Studio Code, which is more suited for complex projects but requires manual setup for ESP32 and libraries. Since we're using Arduino to code the ESP32 for collecting sensors and accelerometer data, Arduino IDE was the best choice because built-in libraries simplify sensor integration. It also supports C and C++, which makes it easy for coding for real-time data collection. This setup ensures our glove can efficiently process ASL gesture in real time while maintaining low power consumption and fast communication with our Android app. This flow chart outlines how Signflex processes the ASL gestures. The glove sensors and a smartphone camera captures the user's hand movement. The system pre-processes the data using OpenCV and normalizes sensor reading. The AI model classifies the gesture by analyzing both image and sensor inputs. The recognized signs is sent via Bluetooth to the mobile app. The app displays the translated text and provides a speech output. And by merging sensor and vision data, we achieve faster and more accurate real-time recognition. To ensure accurate real-time ASL recognition, we conducted extensive software testing. As you can see, a live camera feed testing, which is verified as stable hand tracking under different lighting condition, and also edge detection testing, which enhance hand counters for better recognition. These tests confirmed that our Signflex image processing pipeline works efficiently and provide reliable recognition results. After pre-processing the images to enhance clarity and remove noise, we move into the model training process. To improve recognition accuracy, we trained a deep learning model using ASL gesture images captured while wearing the glove with the sensor installed and actively collecting data, ensuring accurate model training. After that, label data set to map each gesture to its corresponding ASL letter, and a convolutional neural network, CNN, to extract hand movement pattern, which is only designed for image processing and pattern recognition, allowing the model to accurately classify ASL gestures. TF-Lite conversion for Android deployment, making the model lightweight and optimized for real-time processing. And once the model successfully recognizes a gesture, it displays the identified letter on the Android app. From there, the user can see the recognized ASL sign in real time, and the app can convert the text into speech, making communication more accessible and efficient. This process ensures Signflex continuously improves as more data is collected, refining recognition accuracy for real-world use.
Hi, I'm Ryan, and now we'll be talking about the mobile app. The mobile application is a central component of Signflex, acting as the primary user interface between the ASL glove and its users. It wirelessly retrieves recognized ASL hand gestures from the glove, displaying them as text on the smartphone screen. We are focused on a user-centric design because we want it to be visually appealing, intuitive, and fulfill all the design requirements. By prioritizing ease of use, the app bridges communication gaps and furthers our goal of inclusive technology. The core functionalities are real-time gesture display, potential text-to-speech output, and a calibration of settings for sensor thresholds. This slide outlines the logical flow of the app. From startup compatibility checks, Bluetooth setup, loading the gesture library, to main features like translator and library management. If something fails like the connection, the user sees an error message and can retry or close the app. We start with run application, check the device is compatible. If not, it will display an error and then it will exit. If the user has Bluetooth, we attempt to connect to the glove. If that connection works, we load the gesture library. From there, the user can translate gestures in real time or manage the letter gesture library, like adding custom signs or removing old ones. The end goal is to update the display with recognized gestures or to configure the library as needed. While the flowchart gave a top-down logic, the activity diagram shows a sequence of actions and how different actors interact with the system. We have the user or multiple users and possibly the glove or database as external entities. They perform activities like open phone, connect to Bluetooth, open gesture recognition, or store gestures in library. The diamond indicates decisions or branching, like connecting to Bluetooth, and the ovals and rectangles show the start/end or main actions. Arrows illustrate the flow from one step to the next. It clarifies how the user's actions, the app's logic, and database lookups all work in tandem to achieve real-time ASL translation. Here we are comparing Visual Studio Code, WebStorm, and Android Studio, the IDEs we are considered for developing our sign language app. We ultimately chose VS Code because it's free, supports multiple languages, and has an excellent community plus broad plugin ecosystem. WebStorm was great for JavaScript, but it costs money. Android Studio has the best native Android debugging, but it's heavier if you want a cross-platform with React Native. VS Code strikes the balance between all of them. Here we're comparing MongoDB, MySQL, PostgreSQL, and Firebase. This table breaks down ease of use, mobile integration, data usage, real-time capabilities, and maintenance across 4 popular databases. We picked MongoDB for its flexible JSON documents in alignment with the sensor data from the glove. It's relatively quick to set up and handles large or evolving data like custom gestures as well. We recognize that MySQL and PostgreSQL are strong for strict relation data, but we like the schemas approach. Firebase is built in real time, but can be pricier at scale or limiting queries. For here, we have validated React Native, Flutter, Native Android, and iOS for our mobile app framework. Our main focus was ease of use, cross-platform capabilities, performance, and the team's existing skills. We chose React Native because it leverages our team's JavaScript background. It can handle iOS and Android from a single code base, which is crucial for wide device compatibility. Flutter also supported this, but required Dart, which we didn't have experience in, and native approaches would mean separate code for Android and iOS. Here are some example screens of our UI mockup. We have the camera interface for potential vision-based recognition, a document screen for the gesture library, search for finding gestures, and settings for toggling camera access or recognition sensitivity. We wanted a clean layout with a vertical sidebar for switching between major sections, ensuring minimal confusion for the end users. Users can quickly start the camera or connect to Bluetooth for sensor-based recognition, see or edit a library of gestures, search and adjust settings as needed. Now we'll be talking about the administrative. In this section, we'll highlight the behind-the-scenes aspects of our project, such as budgeting, workload delegation, our project timeline, and any key logistical considerations. Here we talk about the financial data. Our projects stand around $360, covering hardware, batteries, electrical components, and other items like cables and shipping and stuff like that. As you can see, most of the money went towards the electrical and batteries, or mainly all the hardware stuff, as the software doesn't really cost much. Our work distribution showed that Maddie and Esteban were the electrical engineers, and me and Antonius were the computer engineers. It shows that Esteban and Maddie are spearheading the PCB design, the battery monitoring system, and power supply unit integration. They're also overseeing the sensor assembly, like flex sensors and IMU on the glove. Antonius is focused on the embedding system, the embedded software in the ESP32, the UART implementation integration, and then dealing with the gesture recognition algorithm while dealing with the confusion and training the model. I dealt with mainly the mobile app development and integrating Bluetooth and combining the sensor and image processing data implementation on the app. This shows our timeline. In weeks 1 to 6, we show that we're mainly started focused on the PCB design and then getting ready for the CDR review check and testing our PCB with assembling it, and then making sure the mobile app should integrate the embedded firmware for real-time data. Weeks 6 to 9, we plan on refining the gesture recognition model, ensuring better accuracy on A to Z while debugging the app and to make sure it handles real user tests. The final stretch is from weeks 10 to 15, and that's when we're just completing our main prototype, preparing for senior design demo, and then the final showcase. Signflex provides an innovative and inclusive approach for bridging communication gaps by leveraging modern tech for deaf to hard of hearing users. We tackled assistive communication challenges from hardware sensor integration to our user-friendly mobile interface. Our final prototype and feature design tool will refine sensory accuracy, Bluetooth reliability, and database syncing. We believe Signflex can serve as a foundation for more accessible communication solutions in the future. Thank you for your attention. We look forward for any questions and feedback you might have regarding our Signflex project.